Okay, so hello again. Now let's go for the third and final lecture, where I'm going to try to introduce finally the basics of numerical relativity and also this Adm formulation in the Hamiltonian formalism for general relativity. So yes, here I again put the references. Yes, I'm taking mainly these references for my analysis, and regarding the Hamiltonian formalism for general relativity, I didn't put the reference here, but it's a paper from 1960s from Adm Equations and Guzman. And now in the previous lecture I just showed some mathematical relations for the 4-dimensional and 3-dimensional Ricci Riemann tensor related with the curvature, with the static curvature. These are called Causative Equations and Cauchy-Maynard equation. They have names after mathematicians because they are very mathematical, but we can use in general relativity because general relativity is a highly mathematical theory. So far we have identified an intrinsic metric and its extrinsic curvature. So what we are going to do is to describe the time evolution of an initial hypersurface, and this initial hypersurface will be determined by the evolution equations of general relativity. However, in general relativity things are complicated because not all the components they are evolved freely. They do not freely propagate because we have constraints in these equations that I previously showed you. So probably for deriving these constraints, it's very useful to have these equations in this form, but some people they do not like this form of the equations. But for deriving the constraints, it's more easy if you know how to apply the mathematics of these projectors. And we will derive these constraints of general relativity when considering Einstein's equations in vacuum. So, as you have seen here, like r mu nu plus, minus 1.5 r g mu nu goes proportional to the matter, yes? But you can rewrite equations in such a way that r mu nu is equal to the matter content, yeah? Some composition of the energy momentum tensor. And then when you are in vacuum, the energy momentum tensor is 0, and then you obtain that the Ricci tensor is 0. So some way of considering general relativity in vacuum is considering the Ricci tensor equals to 0. So that's what I mean that Einstein's equation in vacuum means the Ricci tensor equals 0. And then I can compute a contraction of the Cauchy equation. As you have seen previously, here you have four projectors, and now we have combined them. I have applied one projector to raise an index, and I only have 3 ones. So this contraction of this Cauchy equation is very simple because it gives me the 3-dimensional Ricci tensor, the mean curvature, and the extrinsic curvature. And then an additional contraction gives me almost only scalars. So I get a scalar of which is the mean curvature, the Ricci scalar in 3 dimensions, and this nice contraction of the extrinsic curvature. And here it is important to notice that when I mean K, I mean the K mu nu with the G mu nu, yes, or the gamma. I'm getting this mean curvature by raising this index with a metric. So in principle, this K is different from this contraction. This contraction is something different. It's not this mean curvature. And one can prove that the left-hand side vanishes. This contraction A mu beta nu with this Riemann tensor vanishes, Because you can prove it, like you can expand this projector in terms of the metric and the normal vector, metric, normal vector, and then using the symmetries of the Riemann tensor, you prove that it's zero. Therefore, like just in 3 steps, I obtain from this Gauss-Kodach equation a constraint. And this constraint is called Hamiltonian constraint. Why? Because I think it will be more clear maybe when we go to the Hamiltonian picture, but this is a constraint, and just one constraint that relates. You have here first order time derivatives of the intrinsic metric, and you have something that goes with spatial derivatives. So somehow this is something like getting 3-dimensional Riemann, Ricci scalar, and some things that go quadratic in the K, but this K, this goes proportional to the time derivative of the intrinsic metric. So this is somehow some velocities, square velocities, and something that doesn't have any velocities. This is a constraint, like the constraint in electromagnetism, for instance. And then I take the other equation. I just have 2 equations, which were very complicated. The second complicated one is the Kodach-Maynard equation. And then I expand these projectors here. They are metric plus normal vector. And then I play a little bit. Here I use Einstein equations in vacuum, symmetries of the Riemann tensor. And then I obtain a constraint, another constraint which is different from the Hamiltonian constraint, which is called momentum constraint. And it also somehow gives me relations between the velocities of the gamma. So somehow these equations are not genuinely like an equation of motion because it does not propagate somehow the velocity. It doesn't propagate extrinsic curvature, but what it's doing is constraining the initial values. When I start an initial value problem, I have to give some extra relations that the initial data has to satisfy. And these extra conditions are the constraints. So this is precisely the problem with general relativity, that you have some constraints in the theory and you cannot just choose any set of coordinates and evolve them with Einstein equations, because you also have to take care that the initial value that you give to the metric, how it's going to evolve, you have to satisfy these constraints. And these constraints, they are directly related with diffeomorphism invariance. So it is some other way of taking a look at the diffeomorphism invariance of general relativity, which turns out to be very complicated in numerical analysis. So these constraints, they also appear, of course, in the Hamiltonian formulation of general relativity. And these two constraints, there are 4 constraints, because this is one constraint of only scalars, and these are 3 equations, because these indices, they go special. These derivatives go spatial finally, and these also go only spatial. So it is 3 constraints, 3 momentum constraints, 1 Hamiltonian constraint, then it's 4 constraints. These 4 constraints involve the intrinsic metric, the extrinsic curvature, and the spatial derivatives. And so these are conditions that my initial data has to satisfy to just be able to evolve in time equations. And yes, the initial data cannot be prescribed due to the existence of these constraints in general relativity. And this is just the constraints. Now we have isolated the constraints, and now we want to see what are the real evolution equations. What are the real dynamics of general relativity. And this we can find by computing the Lie derivative of the extrinsic curvature. So I already showed you in the previous slide what is the Lie derivative along a vector. So I take Lie derivative along a vector, of the extrinsic curvature, obtain a relation with spatial derivatives on the Laps function, extrinsic curvature, and four-dimensional Riemann tensor. Therefore, here I have some sort of dynamics because this has time derivatives and of second order, and here I have time derivatives of first order, and here I have somehow a time derivative of an object that is supposed to be dynamical. And then, as I also showed you previously, I have a normal vector, but the normal vector does not necessarily go in the direction of time. So the normal vector has to be shifted somehow in order to go in the direction of the time. Yeah, like normal vector and time go in somehow different directions, and this difference is this shift function that I had to define in the previous slides. And this time vector propagates the coordinates from one time slice to another. This means like the normal vector doesn't always hit in the same coordinate that I started. Then the time vector, it always hits in the same coordinates. So that's why we prefer to use this time instead of the normal vector in the Lie derivative. And then this is precisely the time that I need to evolve the equation. So finally, after doing all the mathematics, because basically the Lie derivative of n is equals to Lie derivative of alpha t plus Lie derivative of beta. So this is precisely because, well, there is a minus sign. So there is a minus sign. But the normal vector I can express in terms of the time, and then the beta, and I can express the Lie derivative of this vector in terms of the Lie derivative of this other vector times alpha plus Lie derivative of the shift. Yeah, just using some properties of the Lie derivative, mathematical properties, and then using mixing all the equations that I showed you previously. We already removed the constraints, so now we can just be left with the dynamics, and what we get is dynamics for the intrinsic metric and the extrinsic curvature. Yes? So these equations are the equations that I need, that are full equivalent to Einstein equations in vacuum, and that I can use to solve any problem in general relativity that I want to use. Yes? So this is what are called Adm equations, and I just obtain them from a Lagrangian point of view. Yeah? But I can also obtain the same equations from the Hamiltonian point of view. So I will show you both. Why? Because also in the Hamiltonian picture, we get maybe a better feeling of what are the constraints. Yeah? The thing is that one could use these equations, these Adm equations, to solve general relativity in a computer. The problem is that this system of equations, it has a problem of solvability because it is what is called a weakly hyperbolic system of partial differential equations, which might create some trouble for numerical resolution. So one, at the end of the day, needs to make some tricks, mathematical tricks, to redefine this set of equations that turns out to be strongly hyperbolic. Yeah? And then one can make numerical computations safely. And this approach, where this system of equations becomes strongly hyperbolic, is called like BSSN OKI formalism. And I will also show you this approach at the end. But I think first, first I want to show you the Hamiltonian formulation of general relativity. And the Hamiltonian formulation is always like very useful. For instance, if you want to go to quantum gravity, you would like to know what is the Hamiltonian of your theory of gravity, and then quantize your metric. But as we know, general relativity has the problem of time that the constraint, the Hamiltonian, which is the energy of your system, Hamiltonian means like the energy of your system, this Hamiltonian is a constraint. It is like weakly zero or strongly zero, as you want to call it. So somehow it doesn't give you any evolution for the metric, like at least in the classical level. Let's say in the quantum level, if you quantize all the things, if you imagine like the Hamiltonian of general relativity like quantized, you don't get any proper quantization of gravity. So that's one way of the many ways of understanding why gravity cannot be, let's say, properly quantized. You can do quantum field theory in a curved spacetime, for instance. Just putting your quantum fields in a curved spacetime, which is not quantized, and you can do that. But if you want to consider like spacetime as a thing that you quantize, then it gets more complicated. So now, for Hamiltonian formulation, as I showed you in electromagnetism, you have to separate somehow space and time. We had this a mu vector, right? We have the a mu, and we have to split in A0 and AI. This is basically the 3+1 split that we did in electromagnetism. In general relativity, it was a bit more complicated because we have a 4x4 matrix. So this split is a little bit more difficult. And in particular, we have to do this split not only in the fields, but also in the Lagrangian. So in the Lagrangian of general relativity, this is the Lagrangian, let's say, times the square root of minus g. This is the Lagrangian of general relativity. So you can split it in the three-dimensional Ricci, the extrinsic curvature, and this mean curvature. And probably an important point here is that this expression is valid once I integrated out boundary terms. There are some boundary terms in this derivation that I did not take care here because I then later put this in the action. So any boundary term that is extra here, it will be integrated away with this integral. Yeah. So that's why I didn't put boundary terms. And then we see here that like physically can be interpreted somehow like the Ricci scale in 4 dimensions. It is some sort of kinetic term. We have here some sort of kinetic term because the k goes with the time derivative of the metric. So this is like x dot square. And this is some sort of potential because it doesn't have any time derivatives. So this is some sort of potential. Yeah? Like somehow some classical interpretation for general relativity. We write our Einstein-Hilbert action in 3+1 decomposition like this. And now it's easy to go for Hamiltonian formulation because we just define our canonical momentas as a variation of Lagrangian with respect to time derivatives of the G00 component. And this is the variation of Lagrangian with respect to the G0I components. And here I am immediately using the Adm decomposition because also, if you remember, just to be exhaustively clear, I showed you like the G00 was alpha, G0I, I decomposed like beta I, and then, yeah, I think this is like with the lower indices, goes like gamma ij, if I'm correctly. So these are just the components of the metric once I did this Adm split, 3+1 split. So with this split, I can define the primary, the canonical momenta, but it turns out that the ones that are related with the G00 and the G0I, they are 0. So these are primary constraints. In the same way that in electromagnetism, I got one primary constraints, in general relativity, I get 4 primary constraints. And all the other remaining momenta, they can be solved in terms of the velocity. They are all independent, let's say. They don't have any, are not involved in any constraint. So these all pi aj that are left, they depend on the velocities and they can be inverted. Yeah? So I can express velocity of my hypersurface intrinsic metric in terms of the momenta, and some spatial derivatives of the shift, which do not matter too much because they are just spatial derivatives, do not involve any kinematics. And yeah, and here, like the intrinsic curvature can be written in terms of time derivative of metric. Yeah? So this is all our momentas of general relativity. And now if we remember the diagram I show you, first we have the Lagrangian, then we define the momentas, then we go for finding primary constraints, and now we want these primary constraints to be preserved in time. So for preserving constraints in time, we need the Hamiltonian. And this is precisely the gravitational Hamiltonian. This is like q dot pi minus L, and I'm adding the primary constraint that I just found. This is everything that you find in the Hamiltonian. But I already know the Lagrangian for general relativity. I just showed you here, right? So I just plug what I know. I replace the velocities in terms of the momenta. I do a little bit of math, and I get the Hamiltonian for general relativity in terms of these momentas, which are the p square. Here I get a term which is linear in the momenta, and here I think this should be beta. Sorry, some people they call alpha and beta, and some other people they call n and ni. I think Alexei was calling the alpha, was calling n. The labs, yes, I'm sorry. So this is the Hamiltonian for just a typo. Hamiltonian for general relativity, and we make sure that our primary constraints are preserved in time. But our primary constraints are very simple. Just this equals 0 and this equals 0. Just one term. Yeah? But in this computation, we also need to, we will need other things probably, because then if we get secondary constraints, we have to also compute the secondary constraint with the Hamiltonian. Therefore, it is very good to check out which will be our Poisson brackets. Our Poisson brackets are defined in this way. Here, metric with metric is 0, momenta with momenta is 0, and this is a commutator, not anti-commutator. And finally, the metric with the momenta, I have to take into account that this metric is symmetric in these indices, and this pi is also symmetric. If I just go for putting one term, then I don't make sure that it is symmetric. So that's why I need to add two terms here. So this Poisson bracket is symmetric in these indices and these indices. And not only that, we could also go for putting this index here, index up, index down, index down, index up, and then we will get something different here, yeah? Something related with the metric. So this is somehow the canonical position of the indices. The gamma goes with indices down, the pi goes with indices up. Otherwise, we need to define some other variable properties, which are not hard to get, but why would we complicate things, right? And now, yeah, this is also like some just technical thing that when we have these spatial derivatives, some additional mathematical subtleties will have to be considered, because Dirac deltas that appear here. These Dirac deltas, they get some spatial derivatives, so that complicates a little bit the computations or the interpretation. So I compute the Poisson bracket of the constraint with the Hamiltonian, and that's the time evolution of the primary constraint. So this computation gives me something that looks very similar, very suspiciously similar to the thing that I obtained in the Lagrangian formulation, to the Hamiltonian constraint. So once you go for expressing the explicit curvature in terms of this momenta, you just notice that the explicit curvature is the momenta. Yeah. So therefore, the Hamiltonian constraint that I show you in the Lagrangian formulation, let's say R3 plus k squared minus k mu. And then you see this, and you see that, and you see that they're kind of the same thing, right? Why? Because they are the same thing. Just this I'm writing in terms of the Lagrangian formulation, and this I'm writing in terms of the Hamiltonian formulation. So the existing curvature is the momenta, let's say, in the Hamiltonian picture. And this is a constraint of the theory. It's obtained from the time evolution of this primary constraint with the Hamiltonian. You obtain this, and you would like that this doesn't evolve in time, doesn't change in time. So you impose that this is 0. And you impose that this is 0, and you obtain, therefore, a new constraint, which is called the Hamiltonian constraint. You can also go for rewriting this expression in some a little bit more complicated way, like with the, let's say, with the canonical positions of the indices all up, and then you define this tensor in this way with only metrics, and this is the same as this one. But we have found one constraint. Now there are 3 more to go. And these are fortunately found computing the time evolution of this pi. I compute again the Poisson bracket with the Hamiltonian, and I obtain this more simple expression, which I call Momenta Constraint, and it also looks suspiciously similar to the constraint that I already found, which I'm going to show you. Again, of course, no one remembers all these things. So you got like we get some sort of derivatives of the k. But now we know that the k is the momenta. So these are just derivatives of the momenta. Yeah? And that's precisely what I get here. Here, I just got a special derivative, covariant special derivative of the momenta, which after lowering the index and applying to the metric, it becomes an expression that I showed you before. So this is, I have to impose that this is 0, and this, therefore, they become some momenta constraints. And then, so I started from a set of by A, by 0 by A, by 0 by A, primary constraints. I got C0, Ci, Hamiltonian and momenta constraints. And do you think that we will get something else here? No, right? Doesn't look like, because even in the Lagrangian formulation, I didn't got more constraints. So this is where all this algorithm, Dirac algorithm, finishes. So I found all the constraints of general relativity. So another way of proving it is precisely to check that all the Poisson brackets of this and this with this and this with this are all of them do not produce more constraints. So the way of doing it is to compute the Poisson brackets, and all these Poisson brackets give you something that looks complicated, but here I just schematically put for you, like I compute the Poisson bracket of momenta with momenta, it gives me something with momenta. I get momenta with Hamiltonian, I get something that goes with the Hamiltonian constraint. Then Hamiltonian with Hamiltonian, it gives me momenta. Yeah, you would have expected Hamiltonian, but somehow this is some sort of algebra that is called like the Adm algebra. It is somehow kind of strange because you don't always get like what you will expect. Yeah, momenta, 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 Hamiltonian, Hamiltonian, momenta, and then momentum, Hamiltonian, Hamiltonian. It's some other different sort of algebra, not like the Lorentz algebra or something. So it reflects something deep theoretically in general relativity, in the structure of general relativity, which I don't want to talk because I don't know very much and it's very theoretical. But you just remember this, that's how the constraints of general relativity behave. And this means that I don't get more constraints here. All of what I get from the Poisson bracket, I already know. So there is nothing new in general relativity. So everything, all the constraints I found, these and these are preserved in time, and I count degrees of freedom. So the degrees of freedom are counted like from the pairs of canonical variables gamma and pi, which are symmetric, therefore they propagate 6 degrees of freedom. I remove 4 degrees of freedom from the 4 first class constraints here should be C mu. C mu means C0 and Ci. I get finally 2 degrees of freedom of general relativity, which are related with the polarization of gravitational waves. Remember, I also got 2 for electromagnetism, which are related with the polarization of another field, the electromagnetic field. Yeah, there are different fields, and that's it. For completeness, and also in my analysis of Hamiltonian, in the introduction to Hamiltonian dynamics that I gave to you, I didn't mention Hamilton's equations, but here they are, Hamilton's equations. Yeah, just express time evolution of metrics, time evolution of momenta, and for general relativity. And after some, let's say, some work, you can prove that these are the Hamilton's equations for general relativity. And it turns out that these are equivalent to the Lagrangian equations of motion that I got in the Lagrangian formulation, because both approaches they should give you the same. Yes. So what I show you, the Adm equations in the Lagrangian picture, they are compatible with the Adm equations in the Hamiltonian picture. They are the same. However, still here, we still will have the problem of weak hyperbolicity because the set of equations are equivalent. So therefore, here also it's good to show, like to you, what are the equations of motion of general relativity after the 3+1 split. But then if I want to do numerics, I also have to do something else with this. I need to do some redefinitions. Yeah? And these redefinitions is what I'm going to show you now, like the last thing I'm going to show you. But first, this is a set of first order equations of motion. Like I get first order time derivative on the G is something equals to the metric, the pi, and some spatial derivatives. The time derivative of the pi is equals to spatial derivatives of the metric, and the momentum, quadratic in the momentum. So in a certain sense, the equations of general relativity, they are first order time derivatives in these subjects, but you can see here that you have pi squared. Yeah, this means that they are nonlinear. Like I could get a differential equation that goes like g dot ij goes like some factor of gij, and then that would be like some linear first order differential equations. But the equations of motion of general relativity are a bit more complicated, like a lot more complicated, because they are nonlinear here. Yeah. So that means that even when general relativity looks very nice, when you write Einstein equations, when you make this split, you see the nonlinearity here, and which makes like difficult to find exact solutions. Exact solutions of general relativity are known only for very symmetric configurations like cosmology, non-rotating black holes, rotating like Kerr black holes, magnetic black hole, and all combinations of let's say charge, rotation, mass, and what else? I'm missing exact solutions. Yeah, you can also get some black hole in an expanding universe. That's also an exact solution of Einstein equations. But what happens if you want to model like a black hole that is rotating and it has some matter around, like an accretion disk, for instance? That's something that happens in nature a lot. And we don't have exact solutions for that. So that's the reason that if we want to do something like we observe in nature, we have to deal with this nonlinearity of the equations, of Einstein equations. So probably here we are going too fast in the sense that you have not even seen yet the exact black hole solution. So that's the reason I cannot go too much beyond this approach, because you still don't even know a black hole solution. So, but when you study black holes and then you get more interested in the topic, then you will see, like the real form of general relativity is this one, not the one that my teachers are presenting. This is like the real, not so nice shape of general relativity, but still it is some first order set of equations. And we can still cast the system in some more simple way, well, like artificially simple, if we express the time derivatives of some variables. Like I can express the system like maybe a little bit simpler if I express time derivatives of objects, and these objects I define, for instance, the is A is the spatial derivative of the lapse, this D is the spatial derivative of the metric, and then I can express the system like a linear system of equations, yeah? Not nonlinear. I can express the system like linear, yeah? And maybe that's a little bit more simple for the eyes, but also this system is weakly hyperbolic, yeah? And what one has to do? One has to do conformal transformations. But first, about hyperbolicity, probably yes, this is something that I mentioned, I didn't explain too much. So you can consider a first order system of equations. This is just mathematics, yeah? It's not general relativity. So you got some function, time derivative of the function, plus spatial derivative of function, times some, let's say some characteristic matrices are called here. And all this system is equal to a function of u. In general relativity, this goes like u squared, for instance. So it is nonlinear, yes? And yes, but here in this definition, we are setting it to 0, this let's say, source. And then one can build the principal symbol matrix. Well, this definition, mathematical definition, you can find somewhere, but just this matrix, principal symbol is related with these characteristic matrices, and here you put some arbitrary vectors, and then you can prove that the system is either strongly hyperbolic or weakly hyperbolic if the principal symbol has real eigenvalues and a complete set of eigenvectors for all this n, and is weakly hyperbolic if it doesn't have a complete set of eigenvectors. Yeah? And that's a problem with general relativity. General relativity is in the Adm formulation is of this kind, and we would like to find a system of equations, of differential equations of this kind. And for that, the most widely used formulation in three-dimensional numeric codes is based on the BSSM-OK formalism. And you can see from the time that these papers have been published that it's not so old, right? I mean, general relativity was proposed 1915, and now some system of equations that is strongly hyperbolic only 1 year before I was born. Yeah. So that means that numerical relativity is kind of not so old. It's a kind of new, young field. Yeah, and also reflects the complexity of Einstein equations in the full system. And this has been very proven. This system has been proven to be very robust. And I'm going to introduce it very briefly now. So we consider a conformal rescaling of the spatial metric, and where this is a conformal factor. So these conformal transformations are very used, like in physics, for instance, when you go for modified theories of gravity. Somehow you want to add like some sort of scalar field, and this extra scalar field goes with this conformal factor. Yeah, it is like some extra symmetry hidden there. But now we are just using it not to add extra degrees of freedom. Actually, we are using it to extract the degrees of freedom of this and encoding them in some new variables. Yeah? And we can do the same trick with the extrinsic curvature, because the extrinsic curvature can be written in terms of the trace of this tensor and the trace-free part of the tensor. And this trace-free part, we make also a conformal transformation. Yeah? So, in principle, your variables in general relativity, the variables that you work with are the gamma, the intrinsic metric, and the extrinsic curvature, which are equivalent in the Hamiltonian picture to the gamma and the pi. Yeah, these are some sort of your metric and your momentum of the metric. So I make this I make a conformal transformation in this one, and I split the trace of this one, the trace and the trace free part. This is the trace, and this is the trace free part. And then I go for rewriting my constraints. Hamiltonian constraint, I use all this redefinition with conformal factors. I rewrite the Hamiltonian constraint then, and I also write the momentum constraint. I write it in a different way. And then I also have to split the evolution equations, but it turns out that before I had like 6 equations for the gamma. I had 6 equations, and now I isolated an equation for only this conformal factor. So it became like I extracted 1 degree of freedom and I put it in the conformal factor, and this trace free part is 5 equations finally that you get. It has some other dynamics, but if you see clearly, it doesn't have the conformal factor. So somehow I just isolated it from this other part. And that's kind of good, because somehow I kind of identify like what are the true dynamics and the, let's say, the thing that doesn't have any dynamics. And then I can also split the intrinsic curvature also naturally gets, let's say, I'm extracting the trace part of the intrinsic curvature in this equation, and the trace free part in another equation. Yeah. And here, this term precisely, I'm taking the trace free part of this term. How do I extract the trace of a tensor? I just take the tensor and subtract the trace times the metric divided by 3. So if I compute the trace of this tensor, the trace is 0. Yeah. So I extracted the trace from this, and I use this process of extracting the trace here in this term. And then I get evolution equations for this term. So this is intrinsic curvature. This is the metric, intrinsic metric, extrinsic curvature equations of motion. And then also I have to split the Ricci tensor. I also need to do some conformal splitting of the Ricci tensor. So this is a part that will be conformally transformed, and this is a part that it will only get these extra connection functions, which are just spatial derivatives of the gammas. So this, let's say, capital gamma depend on spatial derivatives of the lower gamma, which gives me this R, like something only depending on spatial derivatives. So this is again some sort of potential which only has spatial derivatives. And these conformal connection functions, they have a different set of evolution equations like this. So finally, from this equation that I put you here, these equations, time evolution equations, these time evolution equations, and this Hamiltonian and momentum constraint, you can get all the evolution of, let's say, any physical system that you want in general relativity, but you have to put the symmetries beforehand. Yeah. So usually what one will do is that, for instance, to take this gamma like something conformal to Minkowski, for instance, like in cosmology, the gamma can go like A delta ij, or in black hole solutions, you can get like the first factor can be like go like the R 1 over 1 minus m over R, and then the other term will be like some sort of hypersurface, spherical hypersurface, and so on. Like you have a lot of different geometries here that your solutions will get simplified. Yeah. So I don't have time to show you like some concrete examples, but I'm just able to get here because this is where like I will need like some black hole solution to show you like how it works. But there are some. I mean, now you have like at least you have heard like the main concepts. Like for instance, understanding how people do the simulations, and in particular, numerical simulations of general relativity have long been done on supercomputers, but nowadays they are preparing some codes which allow you to perform some simple simulations on your laptop, for instance. For instance, you can take a look at I think it was black holes at home, and you can like black holes at home, and then this is let's say a project of say researchers where you can simulate things like they have tutorials, for instance, how to make a head-on collision of two black holes. You can indeed simulate this, like in some, I don't remember how much time does the simulation take. I think it's less than 1 hour. In less than 1 hour, you can, let's say, compute accurately the physical situation when you have a head-on collision of two black holes, and you can compute, let's say, the perturbation of the space-time, and so on. And they have this simulation in the webpage. Like they say, you can do it like you can do it yourself. You can program it yourself. Yeah. The thing is that for understanding the code, for getting this collapse of black holes, you really need to know where, because here there are a lot of symmetry considerations that you consider. Yeah. And all these symmetry considerations, they greatly simplify all the equations that I showed to you. But still, things like the Hamiltonian and the momentum constraint, they are considering for restricting the initial data that you take here. So anyway, now you know from both the Hamiltonian and the Lagrangian point of view how we get these constraints and why are they so important? Because they restrict your data, your initial data. You cannot take any initial data. They are constrained by the constraints. So this is like some sort of theoretical overview on numerical relativity. Why do I think this topic really needs like more research or more interest, like in at least in students? Is because all the corroborations of general relativity that we have, they are from weak field, slow velocity regimes. Yeah. So general relativity is a theory that can describe very violent phenomena in nature, for which we don't have testing, let's say, either with the theory or with observations. Nowadays, we are getting like the first events in nature that allows us to test general relativity in high, let's say, high velocity strong field regimes, like collisions of black holes, collisions of neutron stars, and so on. And for instance, also the gravitational collapse to black holes and neutron stars, let's say just one isolated star that becomes a black hole or a neutron star, is also a process violent gravitationally, which can be tested, which should be tested with the strong field regime of general relativity. And for this strong regime, unfortunately, analytical solutions are too simple for describing. But nowadays, with the advent of supercomputers, we can start to tackle these scenarios. And I would say even with computers, one can start doing some, let's say, study of these regimes, because the computational programs for modeling this phenomena, they are getting better and better. I just showed you one example of how to define Einstein equations for preparing them for putting in a computer, but this is an active field of research. There are other definitions that you can do, other, let's say, definitions of variables that can give you a better set of equations for solving. Yeah? And I'm again missing I had another slide but doesn't appear. I don't know how to fix it. Well, it was some more motivational words. You know, like it appears like 29 or 30, but it should be, there should be a last slide. Yes, that's it. We have seen, of course, that the qualitatively Einstein equations are similar to some other partial differential equations that appear in physics, like fluid dynamics, magnetohydrodynamics, aerodynamics. But the problem with general relativity has unique additional complications. For instance, in the choice of coordinates, like you can just start with a choice of coordinates describing some system, and it turns out that to be bad because singularities appear in the equations. Singularities is, for instance, in cosmology, here, what happens when the A goes to 0? You have a singularity, right? I mean, everything goes to 0. So that's some, let's say, prediction of general relativity of singularities that you cannot get rid. Can you get rid of that?
That's not how it is. That's the use.
Yes, yes. General relativity has two kinds of problems. Real singularities, like this one, and the one that appears in the center of black holes, and fake singularities, which appear because of the choice of coordinates. So here, there is nothing wrong with the choice of coordinates. There is indeed some singularity there. But in black holes can happen that you choose the coordinates and you get some singularity, for instance, in the event horizon of a black hole. It is known, like the Schwarzschild solution, you get some, let's say, singularity there, which is just a coordinate singularity, and you can remove by another choice of coordinates. So it also happens in the equations of motion that you get some choice of coordinates, and turns out that you get some fake singularities, so that's a big problem in general relativity. Another complication, a little bit more technical, comes from these waveforms I showed you in the first lecture for predicting the emission of the gravitational radiation of colliding black holes. It has a little bit of problem because what you get is the evolution of everything, not just the extracted signal. So all these waves are just hidden in a background simulation, and for removing this background, you need to check how your gravitational field behaves very far away from the source. So you get your collision here. Let's say the collision appears to happen here, and then this produces a pattern of gravitational waves which extends all over time. So you need to know how your gravitational field behaves here in order to remove this background of the event that happens there. But numerically speaking, this is very difficult because then you need to simulate not only what happens here, but what happens at, let's say, megaparsecs away. And having a simulation of megaparsecs is something I think you don't need to do it to know that it may require a lot of computational resources. So this is also another problem, and probably other problems, of course, of numerical relativity, but people are working on this. And probably also something that I didn't mention, people that are going for beyond general relativity, all these problems of singularities, Big Bang, black holes, people think general relativity is not the true theory of gravity, that we need to go beyond. And also, if at some point we have the data for testing these strong energy regimes, and there is some evidence that general relativity is wrong there, we will need to predict which other theory replaces general relativity. So we will need to create these templates of waveforms also for theories beyond general relativity. And if right now we don't know, we still have troubles understanding how works general relativity, like in this set of equations, imagine how it would be for modified theory singularity. That would be quite a challenge, which I think it's one of the fields like one can work in the future. But general relativity has lots of other things to be done, but I think the most promising ones are these because we have the data, and we will have data in the future also to test. So yeah, I think that's everything for today. Thank you. And questions?
Okay, then we should have a short break for the last talk.
Is this runs? Okay.